Okay, so so now let's talk about integral closures of tensor packets and in general. Okay, so definition. So let A be be an inclusion of rings. Okay, so then we just define the integral closure of A and B. So this will be the set of B and B, such that so there exists some f of x and a of x monic, such that f of b is equal to 0. Okay, so this is the integral closure of A in B. Okay, so all right, so there's some really basic. So this is a ring. So this is a ring, and you have to use the Cayley-Hamilton theorem to do this again. And so that's kind of one of the things that you use. And so let me just start with some like exercises that will allow us to build up to showing that the integral closure of so the goal again is that the integral closure in kappa of t is equal to v, where t is this tensor product of, let's say, p-adic rings, and v is the tensor product of sorry, this is not what I want. This will be the direct sum of OL size. Okay, so this is saying that the integral closure of this thing is so what we'll end up writing is that kappa of t here. This is a direct sum of, or a tensor product of the fields, and this could be written as a direct sum of a bunch of other fields, and then you can take the ring of integers of the field and take the direct sum of those, and that will be the ring of integers of this tensor product. So that's what I want to say. So we'll define, this is defined to be one thing, and then we'll show that it's actually the the integral closure. Okay, in the real sense. Okay, so the exercises that we need to do this is that if A1 through A n are domains, so we just do the product version. Okay, so this one's not so hard. With fraction fields, let's say L1 up to Ln, then the integral closure in this product is what you'd expect it to be. So to do this, you kind of take monic, you take elements satisfying monic polynomials. So you take like a tuple, then you have a tuple of polynomials, and then you kind of have to get the degrees to match. So you have to like take the least common multiple of you have to take the least common multiple of the degrees of the minimal polynomials to get this sort of thing to match. But it's not hard to do. Okay, so the other thing is that if A is contained in B, then the integral closure of A in B contains all the idempotents of B. This is important. So like E squared was equal to E. That's a monic. That's a monic equation. So that's easily satisfied. And then the other thing is that if we have three closure properties, then like this, A, B, and C, and if B is integral over A, let's say if let's say our integral ring extensions, then the following holds, that the integral closure of A and C is the same thing as the integral closure of B and C. Okay, so what we're going to do is, for our tensor product example, right, is that we're going to take an integral closure, and then, so okay, well, actually, let's, so this is good. So, so let me prove, yeah, so let's do this. So now let me prove kind of a big theorem. So theorem. And this depends on this fact that so let R be reduced Noetherian, so it has finite number of minimal prime ideals, right? Then so we had this structure theorem for the total field of fractions of R. So we could take the integral closure of R and R. And so this is just, it's always going to be a product. And so it actually breaks up, right, each of these things. So what we'll do is, okay, so the idea is that here, again, you'll have many irreducible components, right? And then, so then you'll take the fraction field of each of the irreducible components, and you'll take the integral closure of the ring of functions on each of the irreducible components of the scheme. Okay, so that's kind of the idea of what's going on. Okay, so so in particular, like R could be connected, and then this thing could be not connected. So after you take an integral closure, things are gonna break apart. All right. Okay, so here's a question: so here's the question: is OK1 OKM reduced? Does it have nilpotent elements? Right? So so let me just say, so let me just show that in general, the tensor product of reduced rings is not reduced, right? Of reduced rings is not always reduced. Okay, and so the example here is to consider something like z adjoin the square root of p, tensor it over z with fp. Okay, and this thing's isomorphic to fp adjoin x modulo x squared. Okay, and then this is not reduced because x, the class of x squared, will be 0. Okay, so so this is something that we can worry about. Okay, so and we worry about this because we want to talk about the total ring of fractions of this tensor packet, right? This tensor product. Okay, so so the claim here, so the lemma that I want to prove is that so the claim is that this tensor product here, the tensor products over, say, if these are p-adic integers, then, or sorry, p-adic rings, and these are rings over the p-adic integers, so this is reduced. Okay, so this is what I want to prove, and so how to prove this, right? Okay, so so like so how do we see that the map is injective? So see that this map OK1 OKM into K1 KM is injective. Like, if we can show that this is injective, then this doesn't have any nilpotent elements, so this won't have any nilpotent elements, right? And maybe it's not the case that this is injective, right? It is, right? And let me show you how that works, right? So the thing is to not think about it tensor-wise, but use another presentation, right? So the wrong way, so here's the wrong way to do it. So you look at this map where you take sums of AIs tensor BIs over ZP, and then you map it to a sum of AIs tensor BIs over QP, right? So this is confusing, okay? Okay, so the right way of doing this, or the easy way, right, is to write each element here as a primitive extension. So where Fi is irreducible and monic. And okay, and so this thing exists, okay, for p-adic fields. Okay, then we'll have that OK1 OKM. Well, this looks like a product of, so it looks like a tuple like this, and then we're modding out by these polynomials here. Okay, and similarly, you know, K1 to Km is also a product, or is also a polynomial ring like this, right? And so this allows us to see this easily, right? So this to see that if this is T and this is V, that that you know, allows us to see that T includes into V, among other things, like as well as things like OKI includes into T and KI includes into V. Okay, and so okay, so as a corollary of the injectivity is that this tensor product is reduced. Okay, and so yeah, so that's something nice. And so the kind of upshot, well, is that we don't have to worry about things with this integral closure. Okay, so all right. I mean, yeah, we can include something, and we can inject it into its ring of fractions. That's what I mean to say. So, all right. So let's start with the. So before we do this, let's do a definition. Okay. So if kappa of R breaks into a bunch of different components, right, is equal to, you know, a sum of kappa of R of EI. So if this is for reduced rings again, I is equal to 1 up to n. Let's say it breaks up into a bunch of different things, so the EI are idempotents. Okay, then we'll define the semi-simplification of R to be the direct sum from I is equal to 1 up to m of REI. And so each one of these, and then this one, I guess, each one of these is the direct sum from I is equal to 1 up to m of Ri, where Ri where Ri is R mod Pi. Okay, so this is actually really relevant for our tensor product example. So we can get this kind of intermediate ring in between the ring of integers and the tensor packet. Okay. Okay. So all right. So here's the proof of the theorem. All right. So each of the idempotents, okay, that we had in that semi-simplification correspond to the component of kappa of pi. So we're using this ei in corresponds. Okay, we're going to take like a basis of the idempotents. So it corresponds to, let's say, of kappa of r corresponds to a component k of pi. So so in particular that we'll have so S REI. So this is isomorphic to kappa of pi. And this is the quotient of the R pi. Okay? So this is the minimal prime ideal. Okay, so this implies, so each of those things are, since, as we said before, EI squared is equal to EI, each one is integral. Okay, and so this means that, this means, implies that the simplification is contained in the integral closure. Okay, so we've already broken it up. Okay, so so since these are in direct sum, right? So since you know, the summands since we have something like this, this thing is contained in the kappa of R, and this is RE1 plus RE2 plus dot 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 plus RER, and this is kappa of R of E1 plus kappa of R of E2 plus kappa of R of ER. So this is contained in here, and it's actually component-wise, right? So we get to apply our product. So we get to apply our product rule. The rule for products, namely that that we have kappa, or so let's say the int. So okay, so we have int of kappa r. So this is the integral closure of the semi-simplification, and so this is now we get to use our kappa of pi, and this is Ri here, direct sum of Ri's like this, and so so here Ri is R mod pi, and this turns into a direct sum of the integral closures. Ri. Okay, and this is exactly what we wanted to show. Okay, So, yeah. Okay, so now we're ready for the application. So here's our application. So we're going to let R be this tensor product of OKIs. I is equal to 1 up to M. Okay, it's reduced. Okay, as we showed before. Okay, then kappa of R, we showed before, was this tensor product here. Okay, and each minimal prime corresponds to an idempotent G psi. Okay, for psi and embedding. So I'm going to use that embedding notation that we talked about this. Okay, and so we'll let. So we're going to define this thing, p psi, to be the annihilator of this G psi. Okay, and so, all right, and now we have that kappa of R. Right, this is by the lemma here. Is this product over size of the integral closure of this product here. So now we have this thing breaks into a product, a bunch of L's. So L size of R mod p psi. Right. So this is the annihilator for R. Right. And so this thing is just the integral closure of this is just what we call the O of L psi. Okay, so in particular, like you could see that like ZP is in here, and so we're taking the integral closure of ZP in this thing. Okay, and so that's so if we're doing it in the local case, and that's all I have to say about that. Okay, all right.